Hello everyone, this is Siddiqur Rahman and welcome to the third and last lecture of the 7th week. So let's start with the learning objective of this lecture. By the end of this lecture, you guys will able to describe or you guys will able to know about flip-flops. This slide represents the overall outline of this lecture, or you can say what kind of topic or the name of the topics which are gonna covered by this lecture are presented in here, such as general overview of this lecture. After this, you can get an idea about the overview of flip-flops along with its classification. After that, you can get an idea about basic idea, or you can say the overview of SR flip-flop. After this, you can get an basic idea, or you can say the idea, or you can say the overview of JK flip-flop, advantages and disadvantages of JK flip-flop, and so many things. So let's start with the general overview of this lecture. The term flip-flop was invented in the year 1918 by the British physicist F. W. Jordan and William Eccles. It was named as the Eccles-Jordan trigger circuit and includes two active elements. The design of the FF was used in the British Colossus code-breaking computer the year 1943. The transistorized version of these circuits were common in computers even after the overview of integrated circuits, though flip-flops made from logic gates are also common now. The first flip-flop circuit was known differently as multivibrators or trigger circuits. Flip-flop is a circuit element where the output not only depends on the present inputs but also depends on the former input and outputs. The major difference between flip-flop circuit and a latch is that flip-flop includes a clock signal, whereas a latch doesn't. From this slide, we may get or we can get a general overview of flip-flop. So let's start. Flip-flops are also the building blocks of sequential circuits. They are made using latches. They are circuits where the output depends not only on the current input but also on the previous inputs. They are also known as memory cells, as they can store one bit of binary data. In fact, flip-flops are the functional memory units in electronics. Flip-flops work on the application of a clock signal. This makes them synchronous. A flip-flop has two inputs and two outputs. The outputs are symbolized by English alphabet Q and complement of Q are complements, and or you can say the outputs are complements of each other. Well, just like a latch, a flip-flop is a bistable multi-vibrator too. It has two stable states. When Q is equals to 1 and the complement of Q is equals to 0, the flip is said to be in a set state. When the value of Q is equals to 0 and the complement of Q, I repeat it again, the value of the complement of Q is equals to 1, in that case you can say, or it is said to be in a reset state. Time has come to learn types of flip-flops, or you can say the classification of flip-flops. So let's start. Flip-flops are classified into four main types. Remember these things carefully. They are, or you can say such as SR flip-flop, which is elaborately called. S stands for set and R stands for reset, which gives us set reset flip-flop. Next one, D flip-flop, which is elaborately called data flip-flop. Well, next one, T flip-flop, which is elaborately called toggle flip-flop. And last one, JK flip-flop, which is elaborately called Jack Kilby flip-flop. Apart from these main types, there are a few modified types as well. That is master slave JK flip-flop. Well, from this slide we get an idea about general overview of SR flip-flop. So let's begin. An SR flip-flop is an extension of the SR latch. So let's take this SR latch inside of the parenthesis NAND gates. Attach the outputs of two new NAND gates to the inputs of the SR latch. Apply a common clock input to the new NAND gates. The other inputs to the first and second new NAND gates are S and R respectively. This is how we construct, or we can construct, an SR flip-flop. The circuit diagram of SR flip-flop is shown in the next slide. So let's start. Let's move. Sorry, I repeat it again. So we need to see the circuit diagram of SR flip-flop. That's why we need to move into the next slide. Well, this slide represents the logic circuit diagram of SR flip-flop. Well, if you look at this figure, then you may find there are three sections. One is left section, another one is middle section, and last one is right section. And in the left section you may find three things: two inputs and one clock pulse signal. And two inputs are symbolized by capital S and capital S English alphabet and capital R English alphabet, and clock is symbolized by CLK. Well, in the middle section there are two things, or you can find there are four NAND gate. Well, and in the left upper middle section you may find first NAND gate, and in the left lower middle section you may find second NAND gate. After this you may find another two input NAND gate, which is named as first NAND gate, or you can say the right middle upper NAND gate, and you may find another NAND gate in the lower portion of the right middle section, which is named as second NAND gate. And in the right section you may find two things. One is output and the next state of the output. Output are named as or called as present state, and the next state of the present state is symbolized by Qn+1, because the present state is symbolized by Qn. And in these things are gonna found above portion, or you can say the upper portion of the right section, and in the lower section of the right side you may find also two things. One is complement of the present state, which is symbolized by Qn bar, and beside this you may find the complement of this the complement of the next state, well, which is symbolized by not qn plus 1. And if you look at the middle portion of this logic diagram, then you may find dotted line or a border which is symbolized or which is designated by a dotted border and which is known as latch. So that's all for SR flip-flop. So let's move into the next slide. Well, this slide represents how many inputs and how many outputs are have SR flip-flop. So we have already known from the previous slide, but as a formality we have to read it again. So let's begin. This circuit has two inputs. One is S and another one is symbolized by S and another one is symbolized by R. Well, and two outputs which are actually symbolized by Qn and not Qn. Well, the upper NAND gate, which is actually left NAND gate, or you can say left upper NAND gate, has two inputs. One is S and another one is clock pulse, and which produces an output, and this output can be used as an input for the right upper NAND gate. Well, and with the complement of present state, which is symbolized by not Qn, produces next state, which is symbolized by Qn plus 1. Similarly, the lower NAND gate, or you can say the lower left NAND gate, which is second NAND gate, symbolized by second NAND gate, has two inputs also. One is capital R and another one is clock pulse, and produces an output which can be used for the input for the lower right NAND gate. Well, and with the present state of Qn, and produces complement of the next state, which is symbolized by not Qn plus 1. So let's move into the next slide. Well, since SR flip-flop has two inputs, one is S and another one is R, that's why we can assign two individual binary number. One is 0 and another one is 1. In that case, we may find four combination of these two inputs, which are 0 0 0 1 1 0 and 1 1. Well, from this slide we can observe when both the inputs are 0, what we gonna found in the next state and the complement of the next state. So let's begin. If S is equals to 1, sorry, I repeat again, if S equals to 0 and clock pulse is equals to 1, or you can say activated, in that case after first NAND gate we found 1, because 0 times 1, which gives 0 to the whole bar, which have whole bar, 0 bar means 1, and in the bottom and from the bottom NAND gate we also find 1, and because the value of R is equals to 0 and the clock pulse gives 1, which provides 0 times 1, which is equivalent to 0, and also the above is bar, the 0 has above, the 0 has also bar, that's why 0 bar is equals to 1. And if we look at the next state, then we are gonna found that then we are gonna found that 1 and Qn bar whole bar, and something is multiplying by 1, which gives something. In this case we get Qn and Qn bar and whole bar, which is cancelled since this element has 2 bar in his head or in his above, that's why according to Boolean algebra this cancels with each other, then we get Qn only. Okay, and if we look at the complement of the next state, we may find 1 and Qn whole bar. Something is multiplying by 1, which gives something. In this case only we get Qn bar. And if we look at the next state, we get if we look at the next state, then we already found Qn, and the complement of the next state should be Qn bar, and which is also correct. So let's move into the next case as well as next slide to explore when one of the input is 0 and another one of and the other input is 1, what we are gonna find in our next state and the complement of the next state. So we need to move into the next slide. Well, this slide represents the second case, which is one of the inputs is 0 and the other one is 1. So let's start with the left side. If s is equals to 0 and clock pulse is the value of clock pulse is 1, in that case after the first NAND gate we found 1, and the lower NAND gate we found 0. Because the value of R is 1 and the value of clock pulse is 1, which is 1 times 1 1, and the 1 bar is equals to 0. And if we look at the next state, which is Qn plus 1, and which have a previous state which is symbolized by Qn, but we need to explore what are gonna found in the next state, which is 1 and Qn bar whole bar. Something is multiplying by 1, then we get something. In this case we get Qn bar as well as another bar. In Boolean algebra we know that if an element has 2 bar over his head, in that case they cancelled with each other. In that case we get that element. In this case we get only Qn. And in the and if we look at the complement of next state, then we are gonna found that 0 and Qn whole bar, something is multiplying by 0, which gives us only 0. That's why we have written here 0 bar, and according to Boolean algebra 0 bar is equals to 1. Well, one thing or one question may arise in your mind. The value of next state is Qn, so you can assume that the complement of this next state should be Qn bar. Okay, you can assume that Qn what we have gonna found in the next state, which is Qn, the value of Qn is equals to 0, and if we complement 0, then we can we are gonna found 1. So I hope there is no confusion about this issue. So let's move into the next slide and explore the next case, which has s is equals to 1 and r is equals to 0. So let's move into the next slide. Well, this slide represents the case 3 of SR flip-flop, which is actually s is equals to 1 and r is equals to 0. So let's start from the left side. When s is equals to 1 and the clock is equals to 1, in that case, after completing or after passing the first NAND gate, we can get 0. And if we look at the lower NAND gate, we can find the value of r is equals to 0 and clock signal is 1. In that case we get 1. And In the right section we may find two things. One is present state and another one is complement of present state, but we need to uh, find out or explore what we have found or what we are gonna found in the next state. Well, if you look at the next step, then you may find which is qn plus 1 is equals to 0 and qn bar whole bar. Well, something is multiplying by 0, that gives us only 0. That's why we have written 0 bar only. According to Boolean algebra, 0 bar is equals to 1. That's why we have written 1. No problem. And in the lower portion of the right side, you may find complement of the present state, and the complement of the next state we are gonna find qn plus 1 bar is equals to 1 and qn whole bar. Something is multiplying by 1, then we can get on that element that are but in this case we may find qn bar. And here another question may arise since in your mind another question may arise in your mind, which is qn plus 1 is equals to 1. So if we complement in this state, then we are gonna find 0. Well, since we found qn plus 1 is equals to 1, then qn plus 1 whole bar must be 0, which is qn bar is equivalent to 0. So let's move into the last case, which is when the both inputs are 1. So let's move into the next slide. Well, this slide represents the case number 4, which is, or you can say the combination of 4, which is when s is equals to 1 and r is equals to 1. So let's start from the left side. When s is equals to 1 and the clock pulse, the value of clock pulse is also 1, we get, after passing the first NAND gate, 0, and also from the lower NAND gate also when passing, because of the value of r is equals to 1 and the clock pulse is equals to 1. That's why we found 0. Well, and in the right section we may found two outputs. One is present state, which is symbolized by qn, and the complement of the present state, which is qn bar. But we do not require this output, but we need output, but the next state of this two state, what is the next state of present state and the complement of the next state. Well, if you look at the next state, then you may find qn plus 1 is equals to 0 and qn bar whole bar. As we have already told that something is multiplying by 0, which gives us 0. That's why we have written 0 bar, which gives, according to Boolean algebra, we may find 1. And the complement of the next state, we may find qn plus 1 whole bar is equals to 0 and qn bar is equals to 0 bar, and we get 1. So let's move into the next state. Before going to the next slide, we may say something. In the next state we may found qn plus 1 is equals to 1, but according to general sense, if we complement this state we may found 0, but we didn't get the value 0, we get the same value from of the next state. So let's move into the next slide. Well, the truth table of SR flip-flop is shown as follows. We have already known from the past 4 slides that the value of clock pulse signal always activated, or you can say high, or you can say the value of clock pulse is always 1. The values are changed only in the inputs, which is symbolized by S and R, and we get 4 combination. One is 0 0, another one is 0 1, another one is 1 0, another one is 1 1. And in the output section, we may find different things. When both the input values are 0, in that case we may find output qn, and this state is named or called as no change state. Well, when one of the input is 0, which is s is equals to 0, and the other one is 1, which is r is equals to 1, in that case we may find in the output section 0, and which is named as reset state. Well, when the one of the inputs is 1, which is s is equals to 1, and the other inputs is 0, in that case in the output section we may find, or we got actually 1, and this state is named and called as set state. And when when both the inputs are 1, which is s equals to 1 and r is equals to 1, in that case we may find nothing, because the value of the next state and the value of the complement of the next state are same, but which is unusual. Okay, that's why this state is named or called as indeterminate state. Well, so let's move into the next slide. Well, this slide represents the circuit diagram of second type of flip-flop, another type of flip-flop, actually not second type, and another type of flip-flop which is known as, or which is named as JK flip-flop. And figure 2 represent the logic circuit diagram of JK flip-flop. And if you look at the figure, then you may find there are three sides actually, or three sections: left section, middle section, and right section. In the left section you may find there are three things: actually two inputs and one clock pulse. Two inputs are symbolized by capital English alphabet as well as capital letter J, and English alphabet as well as capital letter K, and clock pulse or clock signal are symbolized by CLK. And in the middle section there are four logic gate, actually four NAND gate actually, and three inputs NAND gate in the left middle section. And in the right middle section you may find there are two inputs, two NAND gate. Well, and in the right section you may find two things: one is outputs and the next state of the outputs. Well, outputs are symbolized by Qn, which is named as present state, and the complement of the present state is symbolized by Qn bar. And the next and in the most right section, or most right side, you may find there are two things also, which is named as next state in the upper section, and in the lower section you may find the complement of the next state, and the next state is symbolized by Qn plus 1, and the complement of the next state is symbolized by Qn plus 1 bar. So let's move into the next slide. From this slide we may learn the input and output of JK flip-flop. We have already known from the previous slide, but as a formality I have mentioned in here for your understanding. So let's start. This circuit has two inputs such as J and K, and two outputs which is symbolized by Qn and Qn bar. The upper NAND gate, which is left NAND gate, has three inputs. We have already seen these things: J, such as J clock pulse and non-designated input, and produces an output which can be used as an input for the next or beside NAND gate, okay, or you can say the right NAND gate. And with the complement of present state, Qn bar produces the next state Qn plus 1. And similarly, the lower NAND gate, which is actually second NAND gate, or you can say the lower portion or lower middle section, has two inputs also. One is K, sorry, not two inputs, three inputs actually. One is K, another one is a clock pulse, another one is non-designated input, and produces an output which is used as an input for the next NAND gate. or you can say the beside, immediate beside NAND gate, and with the present state of Qn, and produces complement state of the next state, which is symbolized by Qn plus 1 bar. So let's move into the next slide. Well, since JK flip-flop has two inputs, that's why we can assign two individual binary numbers. One is 0 and another one is 1, and we get four combination of these two binary numbers, which are 0 0, 0 1, 1 0 and 1 1. And in here we can learn when both the inputs are 0, in that case what are gonna found in the next state and the complement of the next state. When, so let's begin with the left side. When z is equals to 0 and the clock pulse signal, the value of clock pulse signal is 1, in that case after passed the first NAND gate we may find 1. Similarly, if we passed the second lower, or you can say the lower NAND gate, or then you may find also 1, because the value of k is equals to 0 and the value of k as clock pulse is equals to 1. So something is multiplying by 0, which gives a 0 bar, and according to Boolean algebra we may find 0 bar is equals to 1. And if we look at the right section, you may find two things. One is two things means two output. One is Qn and another one is Qn bar. But we need to require, or but we need to look after the next state and the complement of the next state. So if we look at the next state, which is Qn plus 1 is equals to 1 and Qn bar whole bar. Something is multiplying by 1, which gives that element only. That's why we get in here Qn bar whole bar, which means Qn double bar. In Boolean algebra, an element has two bar over his head, then it cancelled with each other, and we get only that element. So that's why we get in here only Qn. Well, and if we look at the complement of the next state, then we may find 1 and Qn whole bar. Something is multiplying by 1. In that case we get that element. That's why we get in here Qn bar. So let's explore the next case, which is one of the inputs is 0 and the other one is 1. And let's move into the next slide and see what are gonna found in next state and the complement of next state when one of the input is 0 and the other one is 1. So let's move into the next slide. Well, this slide represents the second combination, or you can say when the value, or you can say case number 2, when the value of z is 0 and the value of k is equals to 1. If the case is this, then we have start from the left side. If the value of j is equals to 0 and clock signal is equals to 1, then we may find after past the first NAND gate only 1. Well, and the lower NAND, if we pass the lower NAND gate, then we may find Qn bar. Well, because the lower NAND gate has three inputs. The value of one input, which is k, is equals to 1. That is no problem. And the other and the second input has the value of second input is also 1, which is the clock pulse signal value. And the last input, which is come from the complement of the present state, which is Qn bar. So that's why if we multiply something, if we multiply by 1 something, then we get only that element. In this case we may found Qn bar. And if you look at the next state, which is symbolized by qn plus 1, then we may find, or we will get 1 and qn bar whole bar, which gives qn double bar, and according to the Boolean algebra we may find qn only. And if we look at the complement of the next state, then we may find qn bar and qn whole bar. In that case, according to the Boolean algebra, according to Boolean algebra, we got element and not element, or element bar. Then we have got 0 bar, which gives us 1. And a question may arise in your mind, which is the next state value is qn. The complement of the next state should be qn bar. Okay, that is absolutely correct about your thought. There is no doubt. But since we get the complement of the next state is equals to 1, that's why we assume that the value of next state, which is qn, is assumed to be 0. So let's move into the next case, which is one of the input is 1 and the other one is 0, and we would like to explore what are gonna found in the next state as well as the complement of the next state. So let's move into the next slide. Well, this slide represents the third combination, which is j is equals to 1 and the other input, which is k, is equals to 0. Then what are gonna found in the next state and the complement of the next state. So let's start in the from the left side. When j is equals to 1 and clock pulse, the value of clock pulse is equals to 1, and the third input is qn bar, and we have already known that something is multiplying by 1, we get something, or especially that element actually. That's why and this gate is NAND gate. That's why we get qn bar whole bar, and according to the Boolean algebra we get only qn, and in the lower portion or lower NAND gate we found 1, because there is the one of the input value is 0. And if we look at if we look at the next state, then we may find qn and qn bar whole bar, which gives 0 bar, and which is equivalent to 1. Well, and in the lower portion, which is the if we look at the complement of next state, then we may find qn plus 1 whole bar is equals to 1 and qn bar whole bar, which gives qn overhead double bar, and according to the Boolean algebra we get qn. And here also the same words from the previous slide. So let's move into the next case, which is both the inputs are 1, and we need to move we need to move into the next slide to explore what we have been going to find or found in the next slide, next state actually, not next slide, next state, as well as complement of next state. So let's move into the next slide. Well, this slide represents the fourth combination, which is the value of j is equals to 1 and the value of k is equals to also 1. So if we look at the if we start from the left side of this circuit, then we find the first NAND gate has 3 inputs. The upper NAND gate, you can say the left upper NAND gate has 3 inputs, which is j is equals to 1, clock pulse is equals to also 1, and the last one is qn bar. And we get, after passed the first upper left NAND gate, which is qn double bar, which is equals to qn. And if we passed the lower NAND gate, then we may find qn bar only. And if we look at the next state, then we may find qn and qn bar whole bar, which is equals to 0 bar and which is equals to 1. And if we look at the complement of the next state, then we may find also 1, but which is not correct, or which is not usual actually. So let's move into the next slide. From this slide, we may learn the truth table of JK flip-flop. And if you look at the inputs combination, and when both the inputs are 0, then these states are named or called as no change state. And when both the inputs in actually 1, then we can name this state as toggle state. And when j is equals to 0 and k is equals to 1, then we can name this state as reset state. And when one of the input actually j is equals to 1 and k is equals to 0, in that case we can call this state as set state. And one thing you need to remember, clock pulse is always activated, or you can say the value of clock pulse is also 1. So let's move into the next slide. Well, from this slide we may learn from this slide we may learn the advantage and disadvantage of JK flip-flop. So let's start. There is an advantage of JK flip-flop which is given as follows. It removes the not allowed condition present in the SR flip-flop for an input of SR is equals to 1, 1. Or you can say the value of S is equals to 1 and the values of R is equals to 1. Or you can say both the inputs are 1. In JK flip-flop, an input of 1, 1 gives a toggle in output. We have already seen from the previous slide, so there is no problem. And there is also a disadvantage of this flip-flop. So let's start. There is a disadvantage of JK flip-flop which is given as follows. Something known as race round condition is created in the JK flip-flop. Well, this condition presents itself at JK. The value of JK is equals to 1, 1 input. As we know that the flip-flop toggles the previous output in this configuration. However, the problem is that it does not stop toggling. For every clock pulse, the output keeps toggling. So let's move into the next type of flip-flop, which is D flip-flop. Well, this slide represents a generic overview of D flip-flop. So let's begin. A D flip-flop stands for a data or delay flip-flop. The outputs of this flip-flop are equal to the inputs. We can make a D flip-flop using both SR and JK flip-flops. The construction is similar. Only one input is given to the flip-flop. The other input is invert of the input given. Well, we achieve the inversion using a NOT gate or one input NAND gate. Now it is a data or delay flip-flop depending on whether depending on whether the SR or JK flip-flop requires positive or negative is triggering respectively. So let's move into the next slide. Well, this slide represents the logic circuit diagram of D flip-flop, and in the left side you may find only one thing, which is only one input, which is symbolized by D. And in the middle section, or you can say after the input, you may find there are 5 NAND gates, and four NAND gates are 2 inputs and one is NAND gate. Or you can say you can use instead of this one input NAND gate, you can use NOT gate, no problem. And in the right section you may find 2 things. One is outputs, which is symbolized and named as present state, symbolized by Qn, and the complement of the present state, which is symbolized by Qn bar. And after these you may find the next state of the present state, which is Qn plus 1, and the complement of the next state, which is Qn plus 1 bar. So let's move into the next slide. Well, this circuit has, or you can say this slide represents the input output of the D flip-flop. So let's begin. This circuit has one input, which is D, and 2 outputs, Qn and Qn bar. The second NAND gate, left upper NAND gate, which is also known as left upper NAND gate, has 2 inputs. One is S and another one is clock pulse and produces an output which is used as an input for the fourth NAND gate, which is in the figure, an upper right NAND gate, which is also known as, and with the complement of present state Qn bar produces the next state Qn plus 1. Similarly, the left lower NAND gate, which is also known as third NAND gate, has two inputs, D bar or not D or R, and clock pulse and produces an output which is used as an input for the fifth NAND gate, lower right NAND gate, and with the present state Qn and produces complement of next state Qn plus 1 whole bar. So let's move into the next slide. Well, this slide represents the first case of D flip-flop. Since D flip-flop has only one input, that's why we may assign only two numbers. One is 0 and another one is 1. Well, let's start with the value of 0. So when D is equals to 0, which means S equals to 0 and R is equals to 1. And from the left side you may find when D is equals to 0, then we can get S is equals to 0, and the value of clock pulse has always 1 or activated, and since R is the invert of the D, that's why we get 1. Well, after passing a second NAND gate, we may find 1, and if we passed the third NAND gate, we get 0. And if we look at the right side, then we may find, or specifically if we look at the next state, which is symbolized by Qn plus 1, which gives us 1 and Qn bar whole bar, which gives actually Qn. And if we look at the complement of the next state, then we gonna found 0 and Qn whole bar, which gives us 1. So a question may arise in your mind, which is the value of next state Qn, but the value of the complement of next state should be Qn bar. Yes, obviously, you may assume that the value of Qn is equals to 0. I hope if you assume that the value of Qn is equals to 0, then you have no confusion about the issue. So let's move into the next case and next slide to explore what we gonna found in the next state and the complement of next state when the value of input is 1. So let's move into the next slide. Well, this slide represents the second case, which is D is equals to 1. When D is equals to 1, then S is equals to 1 and R is equals to 0. Then we get that after passed the second NAND gate 0, and after passed the third NAND gate we get 1. Well, and if you look at the next state, then we may found 1. And if we look at the complement of the next state, then we may find Qn bar. And here the words are saying like as previous. I don't explain it again, so let's move into the next slide. Well, this slide represents the truth table of D flip-flop, which is represent in here. And if you look at the truth table, then when D is equals to 0, in that case the sub input, which is S is equals to 0 and R is equals to 1, in that case, or in this state, or this state is named as reset state, and if the value of D is equals to 1, in that case the sub inputs are the value of sub inputs are S is equals to 1 and R is equals to 0, and we get or we can say the name of this state is state. So that's all for D flip-flop. So let's move into the next slide. Well, now there are another type of flip-flop, which is T flip-flop, Actually, this slide represents a generic overview of T flip-flop. So let's begin. The T in T flip-flop stands for toggle. This implies that the output will change from the previous value with a change in the input. We can construct it T flip-flop using JK flip-flop. Well, figure 4 represents the symbol of T flip-flop. Okay, and if you look at the symbol, then you may find three things. One is left section, another one is middle section, and the last one is right section. In the left section you may find one input, which is T, and in the middle section you may find JK flip-flop with clock pulse, and in the right section you may find the output Q and the complement of this output Q bar. So let's move into the next slide. Well, this slide represents the logic circuit diagram of T flip-flop. And if you look at this figure, then you may find three sections. One is left section, another one is middle section, and last one is right section. And in the left section, you may find only two things. One is not two things, actually three things actually. One is main input, which is symbolized by T. After that, you may find the clock pulse, and after that the sub inputs, which is J and K. And after the left section, when you enter or when you look at the middle section, you may find there are 4 NAND gates. And more interesting is that the first 2 NAND gate is actually 3 input NAND gate. After this, we use 2 inputs 2 NAND gate. And after completing a middle section, you may go or you may enter the right section, and you may find there are two things actually. First one is outputs, and the complement of the output, which is named as present state, which and symbolized by Qn, and another one is complement of the present state, which is symbolized by Qn bar, and the most right we may found another two things, which is next state, which is symbolized by Qn plus 1, and the complement of the next state, which is symbolized by Qn plus 1 whole bar. So that's all for the logic diagram or logic circuit diagram of T flip-flop. So let's move into the next slide. Well, this slide represents the input outputs declaration of T flip-flop as a formality. So let's start. This circuit has one input. We have already known that from the previous slide, which is symbolized by T, and two outputs. One is Qn and another one is Qn bar. The left upper NAND gate, which is first NAND gate, has three inputs, J, such as J, clock pulse, and non-designated input, and produces an output which is used as an input for the next NAND gate, which is also known as third NAND gate, and with the complement of present state Qn produces a next state Qn plus 1. Okay, and similarly the left lower gate, which is actually known, which is also known as second NAND gate, and has two inputs, K, clock pulse, and non-designated input, produces an output which is used as an input for the next NAND gate, which is also known as fourth NAND gate, and with the present state Qn, and produces complement of a next state, which is symbolized by Qn plus 1. So let's move into the next slide. Well, this slide represents the first case of T flip-flop, which is actually the T flip-flop has only one input. That's why we may assign two binary numbers. One is 0, so that's why we are called case 1, and another case which is actually the value of T is equals to 1. So let's start. When T is equals to 0, then J is equals to 0 and K is equals to also 0. These are the sub inputs. So let's start from the left side. T is equals to 0. In that case, we may find after first the first NAND gate, which is 1, and also after first the second 1. And if we look at the next state, then we may find 1 and qn bar whole bar, which gives qn double bar, which is equivalent to qn. And if we look at the complement of the next state, we may find 1 and qn whole bar, which gives qn bar. And I hope this is understandable, right? Because the value of next state is qn and the complement of the next state is qn bar. So right. So let's move into the next slide as well as the next case to explore what we have gonna found in the next state and the complement of next state when the value of inputs is 1. So let's move into the next slide. Well, when the value of t is equals to 1, in that case j is equals to 1 and the k is equals to also 1. And if we look at the left side of the circuit, then we may find t is equals to 1, j is equals to also 1, clock pulse is equals to also 1, and k is equals to also 1. And if we passed the first NAND gate, then we may find qn double bar, which is equals to qn. And if we passed the second NAND gate, then we may find qn bar. And if we look at the next state, then we may find qn and qn, sorry, I repeat it again, qn and qn bar whole bar, which gives us 0 according to the Boolean algebra rule, and we get 1. And if you look at the complement of next state, then we have found qn bar and qn whole bar, which gives 0 bar, and according to the Boolean algebra rule, we may find 1. And this is unusual behavior, because if we look at the next state, then we may find the value of next state is 1 and the complement of the next state is also 1. This is not possible. So let's move into the next slide. And this slide represents the truth table of T flip-flop. And if we look at the input section, you may find when T is equals to 0, then the sub inputs are also 0. Both the sub inputs are also 0, which is j is equals to 0 and k equals to 0. In that case, the output we may find the output is qn, which is named as, or which is called as no change state. And when t is equals to 1 and j is equals to 1 and k is equals to also 1, in that case we may found in the output qn bar, and this states named as toggle state. So that's all from the T flip-flop, the T flip-flop. And let's move into the next slide. Well, this slide represents some of the advantages and disadvantages of T flip-flop. So let's start. There are some advantages of T flip-flop, which is given as follows. Number 1, this flip-flops has a toggle input and a clock. When a clock is triggered, it inverts the value of flip-flops. They are good for counters. And last one is in Minecraft piston. They are used as they are very small in size. Now time has come to learn some of the disadvantages of T flip-flop. So let's start. There are some disadvantages of T flip-flop, which is given as follows. The state of flip-flop is known only when the previous state is known. They are not available as ICs, hence they are constructed using ZK flip-flop, D flip-flop, etc. So let's move into the next slide, and we are gonna learn from the next slide some of the applications of T flip-flop. So let's move. Well, this slide represents some of the applications of T flip-flop. So let's start. This type of flip-flop is used as bounce elimination switch. Next, this type of flip-flop is used as frequency driver circuit. That means divides the frequency of periodic waveforms. It is used as data storage when the flip-flops are connected in series, in which each flip-flop stores 1 bit information. This type of flip-flop is used as digital counters. It counts pulses or events, and it can be made by connecting series of flip-flops. So let's move into the next slide. This slide represents the overall applications of flip-flops. So let's start. Number one, counters. Second one is frequency dividers. Third one is shift registers. Next one is storage registers, bounce elimination switch, data storage, data transfer, latch registers, memory. And in the next week and in the next lecture, you guys will learn about counters. So that's all for this lecture and for this week. Thank you guys for your attention. See you guys in the next week and next lecture, and wish you guys a safe Eid with your family members. Thank you. Stay safe and stay home. Thank you so much.